Okay. Oh, and I did record yesterday's lecture and I put it up on YouTube, but I think I forgot to put it up on Canvas because yesterday I had a supernatural experience in my car. I realized that we're taking away from class time real fast, but I was on the phone with my best friend from college and I heard a male voice multiple times on coming across the phone. And eventually, before we hung up, I heard it again. And I asked her, like, are you watching TV? Like, do you have somebody in your apartment? And she said she was alone. And then she heard it and I couldn't hear it. And then she heard it again. And then we both heard like a really loud male moan. And so anyway, I forgot about everything I was supposed to do for about an hour because I came into my house like and told my husband and was like almost crying because I was terrified. Yes, it was awesome, Sarah. But I also spent a lot of the weekend in haunted locations, filming some things. Some of y'all know that I perform and stuff like that. So anyway, I was a little afraid that I really ruined my life and brought some things in that I shouldn't. Anyway, okay. Really dramatic. So I had put the thing up on YouTube right before I left work, and I was like, okay, when I get home, put it up on Canvas. But then when I got home, I ended up like burning Palo Santo throughout my entire house, which I've never done in my life. Um, so it's a really weird reason for getting to egg cleansing time. Yeah, probably. Um, so yeah, I should probably try to remember things. FBI guy didn't realize his mic was on. Haha. Yeah, my husband was like, "Are you sure that it wasn't just like some cell phone interference?" And I was like, "It was responding to what we were saying." And I was terrified. I'm one of those people who's really gung ho about like going after those things until something actually happens. And I'm like, "Oh hell no, like this is really bad." So we can talk about this more later. Right now, we're going to talk about NMR. Okay. I didn't expect so many people to be responding positively to that, so that's fun. Yeah, I will happily tell y'all more about that later, anybody who's interested. Okay. So NMR resonance spectroscopy and mass spectrometry, these are ways of determining the structure of, like it says, of an unknown compound. But I think the reason that a lot of this doesn't often click for undergrads is that you're looking at this and you're like, why would I just need to know the structure of an unknown compound? But it's more useful in things like research, like you're running a reaction. Usually, you're synthesizing something that has never been made before. So, like every paper that I published in grad school, I had to have thorough proof that I had made exactly what I was saying that I had made because it had never been made before. I also had to be able to prove it to myself. Otherwise, I couldn't, publish the material. And so that's what all of these spectroscopies are most useful for is when you are actually doing synthetic organic chemistry and trying to figure out, did this functional group transformation work? Even if it's something really simple like oxidizing an alcohol into a carboxylic acid, which is right at the top of OChem 2 material for y'all. Even something really simple like that can be monitored through really easy methods using IR. NMR spectroscopy helps you figure out how carbons are connected. And so if you are creating something very, very large, NMR can, if you can read it correctly, you can decide like there's a CH2 group attached to another CH2 group attached to a CH, and then there's a carbonyl, and then there's a methyl group. Like you can tell that looking at an NMR spectra. And so these tools are incredibly powerful. The development of NMR actually earned a Nobel Prize like towards the beginning of its lifetime. And the same science that's behind an NMR machine is what's behind an MRI machine used in the medical field. I don't know if you've ever had an MRI before. I had one, I guess 2 years ago now. There was a very long period of time where I was under the impression that I had a brain tumor, and it's not a brain tumor. It ended up being much less scary than that. But I had to go get an NMR, and I was like, so this is what I did to every single thing I ever synthesized in grad school, because you're just sitting inside a giant magnet. And that's exactly what is happening with NMR. It's the exact same technology, just accomplishing kind of different things, which is really cool. So if you're going into the medical field and you're like, how is this NMR stuff going to be useful to me? Just kind of think about it more as learning about MRI and just applying it differently. Just like MRI helps you find things within the body and helps you, identify what's wrong. NMR helps you find things in your chemicals, I guess. That was a weak analogy. I tried. Oh, I'm trying to click on the wrong computer. Here we go. Okay. So spectroscopy itself is the study of the interaction of energy with matter. So if you took Gen Chem 2 lab here, probably Gen Chem 2 lab anywhere, you did UV vis spectrometry, you did, actually I think UV vis is the only thing that we do here now. I don't think we add anything else in there, just UV vis. But that's another type of spectroscopy. You're studying the interaction of light energy with matter. NMR spectroscopy is where energy is absorbed by molecules in a strong magnetic field. These molecules and, well, actually the nuclei of atoms put off characteristic energy absorptions with intensities and splitting patterns that are based on the structure of the molecule. Now, this is saying previously in chapter 2, you did IR and mass spec. That's not true anymore. So we're going to talk about IR in a little bit. But IR is a very simple form of spectroscopy that's just based on the vibration and rotation of molecules and the bonds in molecules, which is exactly like using a microwave, essentially, that can help you determine the presence of certain functional groups within a molecule. So on this slide, what I want to talk to you about is NMR shows you the connectivity of atoms. It helps you determine which carbon groups are attached to each other, which carbon groups are closest to your electronegative functional groups. IR can tell you which functional groups are present. So if you know that you have an oxygen in your compound, IR can help you determine the difference between a carboxylic acid, a ketone or aldehyde, and an alcohol. It can help you see those things. And they all have very specific and obvious like tells within an IR spectra. Mass spectrometry is one of the more complicated ones as far as how it works. And some of the videos that I sent you go into a lot of detail on it. The way that we mainly use it within this class is mass spectrometry can be used to determine the molecular weight of a compound. And so sometimes in our practice problems, you're given a bunch of information and you're given a formula, which could be empirical or it could be molecular. And remembering that an empirical formula is a fraction of the whole formula. It's the lowest ratio of all of the atoms within a compound. You can use the mass spec to determine if what you're looking at is the empirical formula or the true formula. So that's how we're going to use each of these. NMR tells us connectivity, IR tells us functional groups, mass spec tells us the molecular weight so that we can figure out the formula. Those are your 3 things that you're going to do here. There are 2 types of NMR spectroscopy that we're going to talk about here. There's actually a lot of types of NMR spectroscopy. Any nuclei that has a odd mass number can actually be observed by NMR. And here we're only going to use proton NMR and carbon-13 NMR. It's worth pointing out right now that carbon-13 is not the highest frequency form of carbon. It actually makes up a very, very small amount of all carbon on our planet. So if you can picture the periodic table, the mass number for carbon is like 12.001. And remember that those mass numbers are an average of all of the isotopes of carbon. So the fact that you only get to 12.001 tells you how very little carbon-13 there is if that's being averaged into that. So carbon-13 is unique for a couple different reasons, and we'll talk about that in a little bit. The source of energy in NMR is radio waves, which have long wavelengths, and they are very low energy and low frequency. When these low energy radio waves interact with the molecule, they change the nuclear spins of some elements, including protons and carbon-13. And then I already mentioned this, only nuclei that contain odd mass numbers give rise to NMR signals. So you can do like fluorine and phosphorus NMR. Okay, so you're going to hear a lot of talk about nuclear spin, and I'm not going to try and force NMR theory down your throat. This is something that was only kind of roughly explained to me as an undergrad, and then we spent a lot of time treating spectroscopy problems more like a puzzle, which I think is a better approach for undergraduate chemistry. And then when I got into grad school and I had to take advanced spectroscopy courses, then I had to understand the theory of NMR. So right now, I'm just going to kind of tell you how it works. This is not something that you have to walk away with being a master of, if that makes sense. I just don't want you to sit here wondering like, but how, but why? I'm going to tell you how and why, and then you can do with it what you will. So when atoms are outside of a magnetic field, all of their spins are random. So remember that you do kind of learn when you first learn about nuclei that they have a pole running through them. They are essentially magnets in their own right. And normally they'll just be random. They're pointing in different directions, they're spinning, they're like little planets. But if you put them into a magnetic field, you all have seen like those Woolly Willy toys, right? Or is that what it's called? It's probably like Harry Harry or something. I just call it Woolly Willy for fun. But you know, it has like the little iron bits and it has a man's face, and then you take the magnet and you can move the iron shavings around to like give him hair, give him a mustache, give him a beard. That's what magnetic things do in the presence of a magnet. They become ordered. Same thing with nuclei. If you apply a magnetic field to nuclei, or you know, matter in general, everything has nuclei, they become ordered. And the NMR machine has a very strong magnet inside. It's actually really crazy. Depending on what type of NMR it is and how automated it is, sometimes you have to get pretty close to it. One of the NMR machines at University of Maryland, where I did my PhD, you actually had to get underneath it and adjust some settings when you were changing which nuclei you were looking after. And I always would forget to take off like at least one piece of cheap jewelry. Like if I was wearing like something silver, nothing would happen. But sometimes I'd be wearing like some, I don't know, some cheap thing from Claire's that I bought in like, I don't know, 1990, or I was 2 years old in 1990. Anyway, or like a hair clip or something. I actually have had like a piece of jewelry like go up to the machine, and I was like, okay, back off. Like it's not a very strong magnet, like it was gonna choke me, but I was like, okay, this is uncomfortable. I forgot to take this off. But it's a really strong magnet. And so when you put these molecules in there, they're going to organize. These nuclei are going to organize based on the magnetic field. So what then happens is, where's my slide that shows this? Maybe I don't have a slide that shows this because I don't usually worry too much about this. So you organize all the atoms, and right now I'm kind of showing you something in my camera. So if you're looking for what to look at right now, I'm using my hands. So if everything is organized, what the NMR does is it puts out pulses of energy. And what it does is it knocks them down, and then it's measuring how long it takes for them to come back up and organize. That's actually what you're observing on the NMR machine. And depending on how close they are to electronegative species, and depending on the identity of the atom itself, they might come up at different speeds. And those differences are what you're actually observing when you look at an NMR spectrum. And so it's essentially like like a Weebles wobble, but they don't fall down situation, or like one of those punching bags, like the scary clown punching thing that like you knock over and it comes back up. That's what's happening in the NMR machine. It's knocking over the nuclei and they're coming back up. So Let's talk about what you actually see in a spectrum. I'm going to show you a spectrum in a second, but I want to go ahead and tell you what you're looking for when you look at it. So the number of signals in the spectrum tells you how many different unique proton environments are in the molecule. So if you have a plane of symmetry in your molecule, you're going to have some protons that are identical to each other. If you don't have a plane of symmetry, then each carbon that has protons on them, those protons are going to be unique. Sometimes protons, even on the same carbon, can be unique from each other. If they're somehow locked into that position, like part of a cyclic structure. So the number of signals in the spectrum is one of the key pieces of information that you get from an NMR spectrum. The position of the signals in the spectrum along the x-axis is called the chemical shift. And this tells you about how close it is to an electron withdrawing group. Usually this is referred to as the magnetic environment because they're each experiencing their own magnetic environment based on their proximity to those electron withdrawing groups, which are typically your functional groups. The area that is actually under the signal, because the signal is going to be some sort of peak, it's going to have empty space inside. The area underneath is the integral. Just like in calculus, the integral is an area underneath a curve. It tells you how many protons are actually being measured and documented by that particular curve. A thing to remember about integrals is that it's not going to say, this is 2 protons. Actually, a lot of your problems do, but in actuality, when you take an NMR and you're looking at your integrals, you have to divide them out and figure out their ratios to each other in order to determine how many protons they're actually representing. So usually you get some like weird numbers like 4.77, and then something else is 9.4. And so you're like, oh, that's a 2-to-1 ratio. That's normally what you see. Y'all are going to see 3, 2, 1, very clean numbers. I think there's only one example where I didn't do that. The multiplicity or the splitting pattern, that means the same thing, of each signal tells you about the protons that are neighboring it. So if you're looking at a specific peak and it's split into a certain number of peaks, that is telling you about the protons on the neighboring carbons, not about the specific proton that it's representing. And the reason why is that if I have my own magnetic field and somebody sitting next to me has their own magnetic field, their magnetic field is actually going to split my magnetic field. And so if I have one person next to me, I'll get split into 2 magnetic fields. That's what happens to the protons. Neighboring magnetic fields affect what you see on their signal. Okay, so we're going to talk about each of these pieces individually. The number of signals is by far the easiest thing to interpret, I think, or at least that's where I decided to start. I don't know if it's actually the easiest for y'all. It's the easiest for me, I think. So the number of NMR signals equals the number of different types of protons in a compound. So protons that are in different environments give different NMR signals. Equivalent protons give the same NMR signal. So looking at this first compound, we have dimethyl ether. We have a plane of symmetry right through the molecule. So all 3 of these protons on this carbon are equivalent to the protons on this carbon. Sorry, I'm going to go into presentation mode so I can draw on this more easily. So these guys are equivalent to these guys. So if you take an NMR of dimethyl ether, you're going to see 1 NMR signal because you only have 1 type of proton present. Does that make sense? Okay, but then you look at chloroethane and you have the methyl group, you have the CH2 group. The CH2 group is much closer to the chlorine. These are totally different hydrogens experiencing totally different magnetic fields. Both in the fact that one is a methyl and one is a CH2, and also the fact that one has the chlorine directly attached to that carbon. So you're going to see 2 types of signals, and so you'll know that there are 2 types of protons. In this last example, we have ethyl methyl ether. We have 2 methyl groups, but these are actually different from each other because even though they are both methyl groups, this methyl group is directly attached to the oxygen. This methyl is attached to a CH2 group. So their different connectivity from each other, the fact that they are not mirror images of each other, means that they are different. So then, since we have 3 unique sets of protons, we're going to see 3 NMR signals. Now you can also see some of this in your cycloalkanes as well. If you have a situation where you're looking at a cycloalkane or an alkene, it's definitely best to draw the structure out in its most 3D form, because these 2 hydrogens are going to be interacting with chlorine in a way that these 2 hydrogens cannot. And so even though looking at this bottom image, we would think that these 2 hydrogens are identical, they're actually going to have very, very different magnetic fields from each other, because one is on the same face as the chlorine and the other type is not. So even though it looks like there should only be 2 types of protons on this compound, there's actually 1, 2, 3. And that's not a super common case that we're going to look at in this class, but it does exist. Same with alkenes. If you look at this version here, you would say like, oh, well, I have a CH2, that's one type of proton, and I have a proton here. I have 2 protons, but that's not the case. You have this hydrogen that's on the same face as the chlorine. You have this hydrogen that's on the same carbon as the chlorine, and then you have this hydrogen that's trans to the chlorine entirely. So you actually end up with 3 unique signals, because each of those hydrogens are experiencing a totally different magnetic field. So with alkenes and cycloalkanes, make sure that you draw it out in 3D and really think about how their magnetic fields are going to be different. And again, rare case. I do not tend to put this on an exam. I'm usually looking more for, can you take the basics of NMR and apply them? I'm not like, ooh, what can I do to really mess them up this time? That's not how my brain works. Even though when you get into OChem 2, you're going to feel like it does. I promise it does not. Okay, this explains the same thing that I just did, and you're welcome to glance at this on your own sometime. So let's actually look at an NMR spectrum. So this is the spectrum of bromoethane. I think earlier we looked at chloroethane as an example. This would be very, very similar. So the protons here are actually already labeled. The signal for proton A is going to be further down to the left because it is closer to the bromine. This is including a lot of information already. Sorry, let's start with the information that we already have worked on. You have your CH2 group and you have a CH3 group. That is 2 types of protons. So we see 2 signals. This signal down here is a standard. When you take an NMR spectrum, it doesn't necessarily know where on our normalized scale those peaks should be. It puts them relevant to each other. And so you usually include a standard like trimethylsilyl, like this one, so that you can say this has this exact ppm, and you can assign it, and then everything else becomes normalized, and you can compare it to literature values. That's the purpose of that. It's usually going to be labeled like this. Sometimes we use chloroform, so you'll see some things like that, and they'll always be labeled with some letters indicating that they're the standard. So we ignore this one, but these 2 peaks count, and these are the ones that are representing our molecule. And we're going to talk about the splitting and stuff in a little bit. So we'll end up coming back to this exact spectrum in a second. Right now, we're just worried about there are 2 signals.
I have a question, like real quick.
Yes.
So you said that the ones that like act the same, they'll just put out 1 signal, right?
Right.
So, like, say if there was like another on the other side of like bromine, like there was a CH2 connected to a CH3, right? Those ones would still like bring up 1 signal because the B would be the same as the B on the right side, right? So how would we know that there was actually like 2 of the same signal groups but on either side?
Yeah.
Like
Sorry.
if we're like doing that spectrum, like it would still ring up as one signal, but how would we?
So that would be based off of your mass spectrum. So you'd have
Oh, okay,
you'd
okay.
have to know the molecular weight of your compound. Yeah. Or if you were given the formula, it might say C4H10O.
Okay.
Sorry, I switched it to an oxygen because bromine can't make two bonds, and that bothered me.
Oh
Um,
yeah, I'm saying like I was just doing a hypothetical example. Like, okay, thank you.
mhm. Yeah, so it takes a lot of information to come up with this. Like when I would do an NMR in grad school, I had an idea of what I was trying to make. And so I was able to look for certain things. When you're doing a problem in class, I have to give you a lot of information. I can actually show y'all um, what the problems look like so that you have an idea of what I'm talking about here. So usually when I give you an NMR problem to work for an exam, or sometimes I give like an extra credit assignment, that's just working NMR problems. Um, you're given a lot of information. You're given an IR spectrum, which we still haven't talked about. Whoa. Okay. Apparently the last thing I did was giant white ink. So I ended up creating a giant white circle just then. Okay. So you have the IR spectrum, which helps you identify some possible functional groups. You're given a mass spectrum that will tell you the molecular weight of your compound. So this is the only thing you need right here is the mass peak. Notice you also have the molecular formula here. You'll also be given information about UV absorption. We'll talk about what that means in a second. Sometimes, if you're not given it, then you can just assume that there's no UV absorption. And then I put these on two different slides so that you'd actually be able to see it. Usually it's all one like computer piece of paper. And then you're also given a carbon NMR and a proton NMR. And the proton NMR will sometimes have the peaks blown up so that you can um, actually see them. Because right now they're so like in the actual spectrum here, they're so tiny that you can't really tell what's going on. So there's a zoom for each peak there. And the numbers are the integrals. So usually you're given quite a lot of information to help you solve the problem. Um, okay, do. Am I going too slow? Because I know some of y'all have already looked at this, but is this okay? Okay. It's gonna start picking up a little bit. I had to do a little bit of background and tell you about my ghost story, but now we're going. Um, where were we? Okay, we were here. Um, so the next piece of information that's really important is chemical shift. So whether something is upfield or downfield indicates their proximity to a functional group. These approximate chemical shifts here, this is a table that some people like to memorize. You really don't need to do that. There are a couple that you can kind of generalize really easily. Um, but if you're one of the people who like feels more comfortable memorizing, that's fine. But really just relative upfield and downfield can be really helpful. Knowing certain things like protons on a benzene are going to live between 6 and 8.5 is really helpful. um, Knowing that protons on an aldehyde are around 10 is helpful. Everything else is really just based on proximity to an electronegative group, and usually you'll have an idea of what that electronegative group is already, because you'll either like be given like bromine in the molecular formula or oxygen. So I don't think you need to memorize the majority of this table. This is probably the only things that you really need to do. Um, yeah, I would kind of leave it at that. Going much further than that is maybe just a little too much. Um, I'd rather you spend time understanding how this works. There's also this really nice visual here that you can use while you're working on problems that can be really helpful. So like your alkyl protons tend to show up down here unless they are directly adjacent to something electronegative. And of course, the closer they get to something electronegative, the further downfield they go. Um, so to illustrate this, Chemical shift, again, is a measure of proximity to that electronegative thing. Those electronegative atoms pull electron density towards them, and electron density actually shields the nucleus from feeling the magnetic field. And so, if you have something electronegative and it's pulling electron density towards it, it removes that shield. And so that's why it ends up more downfield. And we call it literally de-shielding. So this carbon atom here and the protons that are on it are closer to the chlorine. And so they're going to be more de-shielded. So they're going to end up further downfield. So I color coordinated everything here so you can actually look at the peaks. But a proton on methane has a chemical shift of 0.23. If you add one chlorine onto there so that it's chloromethane, that bumps all of those protons up to 3.05. You put two chlorines on there, those two equivalent protons will have a shift of 5.33. So adding on these groups really moves it downfield. For chloroform, which is often used as a standard, that's 7.24. That is so far downfield that if you didn't know it was chloroform, you might think it was a single peak on benzene. Notice benzene has a chemical shift of 7.26. So the power of those electronegative atoms to de-shield those protons is really significant. The other thing that I want to show you is the difference in the effect. So this whole molecule is polar, right? This carbon atom and its proton are going to be de-shielded because of that dipole. But notice they only have a chemical shift of 1.06. And then when you get to the green proton, it's at 1.81. It's really the orange proton that feels the bulk of it. That has the chemical shift 3.47. So proximity to your electronegative species causes you to end up more downfield. Let me see if I did not put bromoethane back up here. So I'm gonna go back here real fast. So taking a look at the spectrum of bromoethane again, we have our two different peaks. We have our CH2 group, and since it's the closest to bromine, it's also the furthest downfield. The methyl group, being the farthest from bromine, is more upfield, closer to our TMS standard, closer to 0. So that's one way that you can determine which peak is which. There are several ways to do that though. So there are multiple tables of information here for you to look at. If, depending on how you take in information, that's why I just gave you so many different tables. So the next thing is the intensity of the signal, the area under signal, the integral. It's proportional to the number of absorbing protons. So all of these integrals are just ratios, and they tell you how many protons are being represented by a peak. We'll go back and look at bromoethane in a second, but this is a really good example. Typically, integrals are given in a ratio. Obviously, a peak can't represent 1.5 protons. That doesn't make sense. So looking at this, you know that you at least have to multiply this times 2. So this could be a ratio of 3 to 2 protons, which is actually what it is. It ends up being 6 to 4. So you're representing your methyl groups on this benzene ring with this peak here. And then the protons that are actually on the benzene are much further downfield, and they are being represented by an integral of 4 protons. So 1, 2, 3, 4. So sometimes you'll be given something like this. Sometimes you'll be given actual correct numbers. I usually give you ones with actual correct numbers. When I learned how to do NMR, I don't know why, but my teacher actually would hand us a ruler and it didn't have any numbers. It just had this little ding here. And so you had to measure the difference between here in centimeters and then divide it out. And that makes me sound 100. I'm not 100. I turned 33 last Monday, but that was, I don't know, I guess just what my teacher felt like doing to us. But anyway, looking back at bromoethane, oh, I didn't give the integral here. but we can figure out what the integral should be. And this is a really good backwards question. What should be the ratio of B to A? What would be the ratio that we would see? If you divide, let's say, B over A, what would that be? So how many protons is peak B representing? I see we're answering in the chat. No, it's not 2 to 1.
Is it like,
Three?
you look at the number of peaks, so there's like 3 to 4?
Not the number of peaks. So we're talking about the number of protons being represented. So how many protons is peak B representing?
Is it 2 to 1?
3.
3 to 2?
Right. So peak B is representing 3 protons. Peak A is representing 2 protons. So 3 over 2, or you could say 1.5 to 1. But that's our ratio. So if we did have integrals being represented on here, it would probably look something like this. So it's like 1.5 to 1, or it might say 3 to 2. So the integral tells you how many protons it's actually representing at that signal. Does that make sense? I see equal amounts of yeses and nos.
So why would it be like, if you said you don't look at like how many like peaks there are, but B still represented 3, but A was cut in?
Oh yeah, we're gonna talk about splitting in a second. Right now, ignore splitting. We're just talking about in the actual chemical structure, peak B is representing 3 protons and peak A is representing 2 protons. The splitting means something entirely different that we're about to cover. And I think splitting is the most difficult part to understand.
I was just saying, like, if we didn't have that formula up there and we were just looking at those lines, you know what I mean?
Oh,
Like,
no, you would never be given this without the integration. I'm asking y'all, since I gave you the formula, to come up with the integration.
oh, okay.
Sorry, yeah, we were reversing the process. Okay, so to answer your question, Brenda, the next thing is spin-spin splitting. So this is the splitting of protons by nearby protons. So the actual splitting pattern, also called the multiplicity, so the number of little peaks that you see within one signal for a certain type of proton, gives you information about how many protons are on the neighboring carbon. So let's look at bromoethane for a second, because this one is a bit simpler. Protons labeled A are split into 4 peaks. The protons labeled B are split into 3 peaks, right? And no, that does not match the formula. What this is telling us is that protons A are attached to a carbon that has 3 protons. And so it's getting split into 3 + 1 peaks. So the splitting pattern is always N + 1 based on your neighbor. So again, protons on this carbon are being split into 4 peaks because next door there are 3 protons. 3 + 1 = 4. So A gets split into 4. The proton, or the signal representing protons B, is split into 3. And that's because on the neighboring carbon, there are 2 protons. 2 + 1 is 3. So the way that you use this information when you're looking at this is A being split into 4 peaks means that neighboring, I have 3 protons. When I'm looking at the peaks for B, it's split into 3. So I know that my neighboring carbon has 2 protons. Or that the sum of my neighbor's protons is 2. What?
I was just saying, is it always going to be true? But you just answered it, so thank you.
Okay. Um, so we can look at, yeah, you can see the splitting on this one. These are not split at all. These are all single peaks. And what that tells you is that none of these carbons are attached to another carbon that has a neighboring or that has protons, or different protons. So look at this methyl group. The only carbon it's attached to is this one. There are no hydrogens on that carbon. So the signal for the methyl group is not split because it has 0 neighbors. Now, the signal for B is representing this one. Over here, it has 0 neighboring protons. Over here, it has 1. But that neighbor is equal to it. And the protons cannot split themselves. So this is a really common thing that you see on a symmetrical benzene compound. If you have aromatic peaks that have no splitting, then you know you have high symmetry in your compound. We'll come back to that in a little bit. Let's look at the actual example for spin-spin splitting now. So we have 2 different protons here in this compound. We have our CH2 protons, and we also have this CH proton. These have names that I can tell I'm going to end up using on accident. When you have a CH, it's called a methine proton. When you have CH2, it's called methylene. So if I end up using those names, that's what I mean. I'm just talking about the number of protons attached to a certain carbon. So the methine proton has its own signal right here, and it's split into 3 peaks. So what that tells us is that its neighboring carbon has 2 protons, and sure enough, it does. Now our peak representing our methylene protons is only split into 2 peaks, it's which is called a doublet. So that tells us that its neighboring carbon only has 1 proton. The terminology that you'll hear is singlet, doublet, triplet, quadruplet, or sorry, quartet. I don't know why I said quadruplet. Quartet. Those are the ones that you'll see most often. So the other thing that I think is best with NMR is honestly that like practice is the only way to do this. So right now, this is a lot of information and it doesn't really seem to add up, especially since you have the answers on the pages a lot of the time, but we're going to apply it pretty shortly. So there's a lot of information here about splitting patterns that you can definitely spend some time on yourself if you would like to. I'm not going to give you super complex splitting stuff. This is about as bad as it would get, where you have like a total of 6 neighboring protons, so you're being split into 7. We're not going to do spin-spin splitting like this, where you have a quartet of triplets. I'm not going to do that. So here's a good example. This compound has several different types of protons. We have protons on this carbon, which are equivalent to these because there is a plane of symmetry through this molecule. Imagine, let's write CH2, CH3 out like this instead of worrying about the methyl group out there. There's a plane of symmetry through this molecule. So HAs, those are both equivalent to each other. The HBs are equivalent to each other. That's 2 types of protons. Then we have our CH2 and our CH3. So we have 4 types of protons. Therefore, we have 4 signals. HA only has 1 different from itself neighbor. So it's going to be split into a doublet. Same with HB. It only has HA as its neighbor. So it's being split into a doublet. And then we have our CH2 group, which is next to a CH3. So it's split into a quartet. Our CH3 is next to a CH2. So it's split into a triplet. This pattern right here is indicative of an ethyl group. And you'll see this over and over. You'll see a quartet and then a triplet in that order from left to right. That is very, very common for an ethyl group. Okay, sorry about the slides that say Top Hat question. That was when I was using Top Hat. And I forgot to remove them before I, oh, yeah, so the question says there are no peaks for the BR. No, we are only looking at the peaks for the hydrogens. Bromine is not going to show up on the spectra, and it's not going to have any splitting. We're only seeing splitting from the protons. So only nuclei that can be observed by NMR. Carbon can also be observed by NMR, but since there's so little carbon-13, you don't usually see splitting from carbon-13. Although in some of these, you can see what are called carbon satellites. No, that one's just a dirty sample. No, none of these samples were clean enough to see carbon satellites. So never mind, we'll just ignore that. So carbon-13 NMR is a little different. There's no splitting patterns. It's just a single peak representing a carbon. So every carbon is going to have a peak on the carbon-13 NMR. And again, their proximity to your electronegative functional groups are going to move them downfield. Notice that the scale of the chemical shift is wildly different. In our proton NMR, the highest thing that you'll see is like 13, 14. Here we go up to 200, 210, 220. But the kind of general range is the same. So if you were to take the similar map that I gave you for proton NMR and overlap it with this one, it would look very, very similar. And you can actually get a lot of information from carbon-13 NMRs, but we're not going to go into that much detail. So if you start seeing like depth and cozy NMR popping up in your like videos or on YouTube, or if you're on like Khan Academy or something, ignore that stuff. We're not doing any of the like decoupled types of carbon NMR. That's just way past what an undergraduate needs. Just so not worth the energy. So again, number of signals is your most important thing from carbon NMR. It gives you a lot of information about the symmetry of a compound. So for example, this is 1-propanol. You have your CH2 group that is closer to your hydroxyl group. Oops, why can't I erase? I'm gonna change my color to something brighter because I feel like you can't really see it when I draw. So the CH2 group is closer to the hydroxyl group, so it's going to be further down field. This next CH2 group is a little farther away from the hydroxyl group, so it's gonna be down here. The CH3 group is the furthest away from the hydroxyl, so it's all the way down here. Same as proton NMR as far as your chemical shifts. And you don't have to worry about splitting. So for this one, let's just assign these carbon peaks real fast. Oh, wait. It's already assigned. That's rude. Sorry, I thought I had a good idea. And I think I did this with my other class too last time I taught it. And I was looking at the markings and I was like, how many times have you done this? And it has the information written on it already. The methyl group shows up at 13.6. That's what those numbers are showing you, is the chemical shift of each carbon. So farther away you are from the chlorine, the lower your chemical shift. So these two being farthest away from the chlorines are down here. This one being a methyl brings it a little further down. CH2, since it is attached to more carbons, it ends up having a slightly further shift. So even though these two are equally close to the carbon, their difference in chemical shift is related to their difference in substitution. So the more substituted it is, the further down the shift is going to be. But notice also this scale is only through 60. This is not the full scale that we're looking at. Oh, accidentally scrolled down as I did that. That was weird. We're now on a totally different spectrum. And I accidentally circled it. That's so weird. So yeah, you can go through these and kind of do this yourself. What I want to do now is start to look at some of these compounds. Why is there now a circle on every slide that I cannot erase? Huh, okay. Well, that's going to be annoying. I'll have to figure that out later. So ignore the red circle that's at the bottom of every single slide. I have no idea why that's there. It's not doing anything for us. What I want to do now is take a look at compound 1 and see if we can pick from our options. I gave you multiple choice for this. Sorry, compound 1. We're going to see if we can figure out from our options which compound is which. And this is how all of your exams will be also. I'm not going to make you draw the structure on your own. In OCHEM 2, I do that. In OCHEM 1, it's multiple choice. So one of the things that you're going to notice right off the bat here is that I gave you all very similar functional groups. So they're all carbonyl containing. And we didn't really get to talking about IR today, and I'd rather spend time working on the problems. So I'll send out a short lecture video on IR and the functional groups that you need to know. It's really not that bad. There's about 5 things that I want you to know about NMR, or sorry, IR. So one of the big ones for IR is this guy right here. If you see a peak that goes all the way down to the bottom and has that shape and it's smack dab in the middle of the IR, this tells you that you have a carbonyl. This could be a ketone, it could be an aldehyde, it could be part of a carboxylic acid, it could be part of an ester or an amide, but you have a carbon-oxygen double bond. That is the only thing that gives you that big, like strong peak that goes all the way down to the bottom, right in the middle of the IR spectrum. So that's one of the big ones. I can't erase anything anymore. That's, okay, I'm gonna have to be really careful about what I draw. That's so bizarre. Now, the other pieces of information that you can get from this is the UV spectrum here. The fact that it's telling you that you have absorbance, I don't need you to know numbers. I don't want you to care about numbers. If it says you have absorbance, that means you have what is called conjugation. And in this class, since we haven't really talked about conjugation yet, any absorbance at all equals benzene ring. Oops, sorry, ring. I can't erase that, so I'm just gonna rewrite it. Any absorbance at all, benzene ring. Can I erase like this? Nope. Okay. I must have really broken my tablet's brain because I can't do anything now. From the mass spectrum, I want you to take this and make sure that this number matches what you get if you add up all of these atoms here. And I'm going to tell you, I'm going to tell you for this one, it does. 9 times 12 carbons, how much does that equal? If you have to multiply 9 times 12.
108.
108. So we are already most of the way there, right? That is a really easy trick. If you multiplied that number and got less than half of your mass peak, you're going to have to multiply your molecular formula. If you multiply out the carbons and you're most of the way to your mass peak, like we got 108 just now, when our mass peak says 134, then you probably have the correct formula already. There's no multiplier of this that would fit within that molecular weight. Does that make sense? Whereas if we had multiplied that out and we got like 60, then we probably aren't there unless we have like 100 oxygens. So that's all you need to use the mass spectrum for, is to determine if this is the molecular formula or the empirical formula. So far, what we know based off this first page is we definitely have a carbonyl, and our formula is C9H10O, and we definitely have a benzene ring, and that's already a lot of information. So, oh my gosh, why is all of my ink carrying over? Okay, that's problematic. 1 second.
You should just try the back button, like the undo at the top next to the save button.
Um,
Like it's a little arrow that's like, "Doop." There's like a
I
back button.
don't, oh, this one right here.
Yeah.
Oh, now I'm on a totally different slide too. What in the world? Hold on, I'm gonna shut this down real fast. No, do not save anything that I just did. Sorry, there's a lot of drawing involved in spectroscopy, and we weren't going to be able to keep playing that game for very long. So with spectroscopy, how many of y'all like to do like Sudoku puzzles and things like that? Yeah. Spectroscopy is your thing then. It is straight up a puzzle. You have to know what information you're getting from the spectra. That's the hard part. But once you have all the information, it is just a puzzle. So if you like puzzles, this is going to be at least something that you mildly enjoy. I realize that it's still for organic chemistry, and that tends to put a damper on most sources of joy for most of my students. But hopefully this is something you end up enjoying. Okay. Okay. Today's chat is really interesting. It's going really well. Okay, so for this compound, this is the NMR page of our information for compound 1. I'm gonna go ahead and write down what we already know. Whoops. Okay. We know that we have a carbonyl. We know that we have a benzene ring because of the UV vis. We also know the formula is, I believe it was C9H10. Oh, yeah, okay. C9H10O. So this is the information that we have, and that's a lot. I'm actually gonna write this up here so it's not taking up as much space. Okay, so from here, it doesn't matter which spectra you look at first. Typically, I think looking at the carbon NMR can give you a really good hint as to the degree of symmetry that you have. Sorry, I have like the hiccups. So first of all, I want to look at this NMR with y'all and just eliminate some information here. So this is marked as the solvent. So you're not going to involve these peaks in your determinations. So we have 1, 2, 3, 4, 5, 6, 7 peaks from the carbon NMR. And we know that we have 9 total carbons. So that tells us that we have to have some sort of symmetry occurring in this molecule. Otherwise, that would not work, right? If there was no symmetry, we would have 9 peaks in our carbon NMR. The other thing that we have is our proton NMR, telling us that we have 5 peaks all being represented by this cluster, this disaster here. If you have 5 aromatic protons, which is what this is telling us, that means that you only have 1 thing coming off of your benzene ring. So I'm going to draw this over here. That's the only way that would work, because you have to have 5 protons on your benzene ring. Does that make sense? So there can only be 1 substitution on your benzene ring. Okay, the other information we have is this group of 3 and this group of 2, and they also don't seem to be splitting each other. We have the formula C9H10O. So we still have to figure out where 2 of our carbons go, and we have to figure out where that carbonyl goes. So if each of these are singlets, what does that tell us? Are these 2 groups next to each other? Do we have a CH2, CH3 ethyl group?
No.
No, they cannot be next to each other. Otherwise, they would have a splitting pattern. Since they're singlets, that's their sign to us that they have no neighboring hydrogens. So we must have a CH2 group connected to a carbon that has no protons and a CH3 group with a carbon connected to that carbon that has no protons. Lucky for us, we need to figure out where to put a carbonyl group. So it must be there. Does this process make sense? Okay, so then our substitution on our benzene ring must be CH2, carbonyl, CH3. And then when you come up with a structure, first of all, make sure that it shows up on your multiple choice options, which it does. The other thing that you need to do is make sure that it matches your spectra, like work backwards just a little bit. I said that there were only 7 types of carbon in this compound. So I need to go through and make sure that I don't have 9 unique carbons in my compound or 4 unique carbons in my compound, right? So this methyl group is unique. This carbonyl is unique. This CH2 group is unique. This one is unique. This one matches this one, so I'm going to give them the same number. This carbon matches this carbon, and then this carbon is unique. So I have 7 carbons. What is the giveaway that there's a benzene ring when looking at graphs that aren't UV spectrum? Let me see if I have an example, because I think if it has benzene, I give you the UV vis. But the other way that you could determine that is by calculating the degree of unsaturation, which is something that you learn around the same time as IR. So I think I didn't cover that. I can go back and I'll add that in when I do my IR video later today. I'll add degree of unsaturation in. Degree of unsaturation is a way of calculating how many double bonds and possible rings you have. So it tells you that you're missing hydrogens essentially, and you calculate that from your formula. So that would be another way to do it. But in this case, you don't have to, because all of the multiple choice options have a benzene. Let me put this back on so I can have a little more control. Sure, let's keep that. Let me see. New compound 2 gives you the UV vis. I'm going to look for an example. So this one doesn't have any benzene rings in it, and it doesn't give you, it says no significant UV absorption. Okay. I also have some practice problems I can send y'all, and I can send you a separate document with the answers so that you can do this yourself and practice. That one does not have multiple choice options though, so it's like a build it yourself scenario. Okay, but remember, when you're doing your test questions, I'm going to give you multiple choice for this semester. So that's where I would start first. So notice all of these have benzene rings. All of these have esters. And all of these, the esters are CH2, CH3. They're all ethyl esters. So what is the only difference between these structures?
Where it's located.
Exactly, right? So it's going to be that plane of symmetry. So the giveaway for these is going to be all in the carbon NMR or the proton NMR, but the carbon NMR is really going to be your big hint. So like there's a plane of symmetry here. So in the carbon NMR for this one, we would see 1, 2, 3, 4. 2 and 3 would be the same. 5, 5, 6, 6, 7, 7. We would see 7 carbons. These 2, A and B, are actually the same. I just kind of rotated them. One of my classes was really mad at me for that for some reason. I can't remember why, but they thought it was like the most devious thing I'd ever done. And I was like, I needed 4 options, and there's only so many ways you can substitute a benzene ring. Calm down. This one, compound C, actually has a plane of symmetry here and here. So this one's a cool example because you have one carbon, two, two, one, two, two. So there are only two types of carbons on the benzene because there are so many planes of symmetry. And then you have 3, 4, 5, 3, 4, 5. So this has 5 carbons. Also, if you're given 2 identical options, it's neither of those. It can't be, right? So I'm all about teaching y'all also some logic for multiple choice tests because when you take OCHEM 2 in the fall, assuming that COVID doesn't completely shut us down again, you will be taking the ACS exam, which is multiple choice for your final. At least that's the current plan. And some of it is going to be like, we didn't necessarily learn that. So you just gotta kind of eliminate options. So really, we're only considering the options between C and D. D has 1, 2, 3, 1, 2, 3, 4, 4, 5, 5, 6, 6. So notice all of these options are actually determinable just by looking at the carbon NMR. Of course, since we're learning spectroscopy, we're gonna take a step back and look at a little more than the carbon NMR. But I want to point out, we know that this has an ester in it. So we know that we are looking for signs of this. So this is your carbonyl sign. This right here is actually a carbon oxygen bond. But really this would be enough to get you pretty far. The molecular weight again can help you determine if this is the correct formula, which it is. The UV spectrum tells you that you have your benzene ring. So that's what you would get from this first page. The CO double bond would be enough if you couldn't figure out the CO right there. Here, oh, I clicked on totally the wrong slide, sorry. Here we are at our carbon NMR and our proton NMR. There are 2 different types of spectra here. Anytime that you have multiple spectra like this, ignore the off resonance decoupled. We did not talk about how to do that. Only ever look at proton decoupled. So if you have multiple spectra, proton decoupled is the one you're looking at. This has solvent peaks. It also has a TMS peak. So cross those out. We have 1, 2, 3, 4, 5, 6 peaks. So then you look at your options. That's compound D. I know I just made that look really simple, and I know that it's not as simple when you're first learning it, but eventually it does get this simple if you practice. And some of the problems can be answered this easily. Usually on an exam, I give 2 NMRs. One of them is a little more challenging, like the first one, where you're actually having to determine some connectivity of atoms. And one is like, do you understand the basic concept of symmetry and how that's represented in NMR? So it's usually 2 situations like that. Okay, our next one, I don't ask you to learn what the nitrile group looks like in IR. So if you were looking at this IR, you would probably be a little stumped, and that's fine. You would see this, and the thing that you'd be most likely to confuse it with would be an OH group, and you would know that it's not an OH group if there's no oxygen in the formula. And no UV absorption, so no benzene ring. So C5H9N is our formula. Okay, so now we need to figure out the difference between these. So notice this has the same functional group throughout. Our thing is going to be looking at symmetry and connectivity of atoms. So again, figuring out how many peaks you should see in your carbon NMR is often a really good place to start. that can help you eliminate some things really, really quickly. So how many carbon peaks should I see from compound A? Go ahead and think about it for a second. And if you can do the other ones as well, go for it. I see in the chat we have suggestion of 3. Brenda, I just read what you wrote about the esters. The answer D gives you beetle energy, and that's hilarious. So how many unique carbons are in this compound? So I see a lot of votes for a lot of different things. Okay, so let's take a look at this. We have these 2 methyl groups. Those are going to be the same peak, so we'll call them 1. We have this carbon here, we'll call it 2. That's going to be different from this carbon here. So so far we have CH3s, we have a CH, we have a CH2, and then we also have our nitrile carbon. So there should be 4 here. Okay, go ahead and try and do B, C, and D real fast. I'm gonna give you like a minute, and then we'll start working on it together. Okay, I see a lot of answers in the chat. Let's go ahead and talk this through. So I think one of the things that we're forgetting is that not all CH3 groups are necessarily equal. Not all CH2 groups are necessarily equal, right? Their proximity to other groups and a lack of plane of symmetry will make them unequal. So these 3 methyl groups here are equal because they are all attached to the same carbon, right? So all 3 of these methyl groups, we'll just call them 1. The carbon that they're attached to is a quaternary carbon. We'll call it 2. And then the nitrile is 3. So there are 3 carbons in compound B. 3 unique carbons, 3 carbon signals. Let's look at compound C. We have this methyl group here. Is this the same as this methyl group? No. Okay. So we have 1, 2, they're different from each other. We have a CH2 group that's different from anything else. We have this carbon with 1 hydrogen, it's methine. And then we have our nitrile. So we have 5 carbons in compound C. And then compound D, I think, caught some of us off guard because we have a CH3 group, and then we have 3 CH2s. But the CH2s are different from each other because this one is directly attached to the nitrile. This one is in between 2 CH2 groups. This one is attached to a methyl and a CH2. That makes them different, right? They're going to have different, albeit slightly different, magnetic environments. So 1, 2, 3, 4, 5. So 5 carbons. So already we can't decide between C and D based on carbon NMR, but we could see if we can eliminate them all together. So carbon NMR, we have our solvent we're going to ignore. We have our TMS we're going to ignore. This says that it resolves into 2 peaks at a higher field, and we'll talk about that in a hot second. But so far, it looks like we have 3 peaks, and that most likely leads to compound B. It certainly does not lead to compound C, and D. Now it says that one of them resolves into 2 peaks at higher fields. So that could mean that there are 4 unique carbons. So we need to keep looking a little more to figure this out. So this one gets a little tricky, actually. It's kind of mean. Let's look at the NMR spectrum, because we haven't talked that much about carbon-13 NMR, and the proton NMR has a lot going on. This will help you eliminate stuff real fast. How many types of protons are there here? Note, these are zooms of what's going on over here, so we can ignore this and focus only on the zoomed part if you want. How many signals do we have here? So remember, it's integrating these together, representing 6 protons. It's kind of 2 different signals representing 3 each. And then we have 1 proton that's being split into a bunch. And then we have 2 protons that are being split into a doublet. Okay, so is that going to match compound B? No, B has 1 type of proton, right? And it wouldn't be split at all. This would just be a massive peak towards the upfield end, the right-hand side, integrating for 9 protons. And we do not see that. Compound B is gone. So already we can see that it's most likely compound A. Let's talk about why. Actually, I'm going to draw compound A on the previous slide so we can. Okay. So compound A has 2 methyl groups, and they are neighboring a carbon that has 1 hydrogen. Let's go ahead and draw. So the 2 methyl groups thing already checks out because this is 6 protons total. That's going to match this guy right here, or let me circle in the area we're looking at over here, right? So that's already a good sign. We also have this 1 proton here. That's going to match this. And then we have a CH2 group. That's going to match this, right? The CH2 group is split into a doublet because it's neighboring 1 proton. So that matches up. The only splitting that's kind of confusing is the one for the single proton. And at this point, we already have our answer, so you wouldn't need to dig into it further. But we can count this, and these little arrows are indicating that these peaks exist. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. This is telling us that we have 8 neighbors. And if you look at this proton, it has 6 from the 2 methyl groups and 2 here. So that lines up. So these spectra confirm for us this. And if we're looking at the carbon NMR, let me label these real fast. We have A, B, and then this says resolves into 2 peaks at a higher field. So C/D. That's telling us that like even though these are equivalent to each other, if you have a stronger instrument, it's going to be able to determine the difference between them. Just because notice, like based on rotation, at some point, one of them is going to be just a little closer to the nitrile in space, not connectivity wise, but in space. That's what that's getting on about. Is just like when it's rotating, you're going to see slightly different magnetic fields, and a higher resolution instrument would be able to show you that. So what carbon is A representing?
Is it the one closer to the nitrogen, the CN?
Right. So this is A. What is B representing?
The next one down.
Yeah. And then these are being represented by C/D. Since this is proton decoupled, the nitrile is not actually going to show up, which is fine. Yeah. So this is one of those cases where you can look at the carbon NMR to help narrow down some options. Like that definitely helped us eliminate options C and D, but you always want to go back and double check, because say we had picked compound B based off of what we saw in the carbon NMR. If just a quick check versus the proton NMR would fix that real fast, right? The proton NMR for compound B would literally be like, here is my, oh, why can't I draw? What do you mean? Okay. Whew. So we would have this single line, or our baseline, and then we would have this. It wouldn't be split. It would say 9 as your integral. Like that would be the proton NMR for B. So it'd be really, really simple. And that is not at all what we saw, right? Okay, so I accidentally took the whole time. It's now 11:40 or 11:39. But spectroscopy is, I don't know, I think it's really fun. I also recognize that for undergraduates, a lot of times you're like, this is one of the things that I don't need. And that's probably true for a lot of y'all. And if you do end up going into organic research or chemistry research in general, you're gonna end up taking an advanced class on this. The thing that you can take away from this, just like with a lot of this OChem stuff, is problem solving. There is never going to be a point in your life where you don't need to problem solve. And honestly, that's one of the big things that you take away from college in general is if you're actually applying yourself in your classes and learning new things, those critical thinking and problem solving skills are incredibly important. And the type of logic that we just used for our spectroscopy problems is really, really important in OChem 2, because OChem 2 only builds on OChem 1 and it gets a little harder. And there is a lot of problem solving involved, especially as we start moving into synthesis problems. So I want you to treat these like puzzles that you're getting graded on, because you are. But also, if this is one of the things where you're looking at this and you're like, I'm never going to get this and I don't want to, that's a choice that you're welcome to make. You're going to end up sacrificing some points on an exam. But if you put that time into your reactions instead, you could earn a lot of points back, right? So make a decision for yourself, but also know that like the value here is problem solving skills, and also some points on exams throughout the rest of your OChem career, because it is part of the curriculum. I do have to cover it, but it's also not integral to the rest of your OChem education, if you want to look at it that way. So yeah, are there any questions before we go? Do not forget to retake the exam 2 if you need to. If you're already happy with your grade and you got to go through the exam and you feel good about it, that's great. It's a good opportunity, so just don't miss it.
Is that quiz still today too, or did that get moved to tomorrow?
Let's not do a quiz because you're already doing an extra exam and there's going to be homework for chapter 9 and 10 open this week. Is that okay if we don't have it?
Yeah, I'm told now.
Okay. I'm still planning on throwing in an extra credit quiz next week. So it can replace your lowest quiz grade. So if you're thinking like, I missed a quiz and I need to be able to bump up my quiz average, we'll do that with that. Yes, I will post this video. I'll also post the one from yesterday. It's already uploaded to YouTube. I just forgot to put it on Canvas. So yeah, thanks guys. See you later.
Thank you.
Mm-hmm.
I mean, I can show you what I have on mine so far too, if that's helpful, but
yeah, maybe after we talk about this for a second, because what I usually find with students making flashcards is that they make flashcards that are so specific or that are not reversible, and making flashcards that are reversible and broad is definitely the best way to approach flashcards if that's your preferred method. So I'm not a flashcard user because I'm not good at memorizing, but combining flashcards with like conceptual stuff can be really powerful, especially because you'll then have to like make flashcards that fit that, and that'll make you analyze the situation a little more. So for example, this is a set of 2 flashcards. On the top, I'm going to put like a bad example. On the bottom, we're going to do a good example for the same reaction. So let's say that what you were struggling with was remembering to do anti-Markovnikov with hydroboration oxidation. And so what a lot of students will do is something like this. They put a really basic alkene, and then they put the reagents on there. And then on the other side, they put this. So the reason that this is not useful is, one, because it's only going to help you learn this reaction, right? There's nothing in this that shows you a pattern necessarily. What it shows you is that if you take one propene, or I guess just propene, it doesn't need the number, and react it with boron THF and follow it up with sodium hydroxide and water, or sorry, it's peroxide, isn't it? Am I mixing things up? Peroxide? Oh, okay. Apparently I can't remember. That's not great. And then on the other side, you have 1 propanol. So that'll help you learn this very specific thing that you'll never see on a quiz or an exam. Also, if you have your flashcard deck and you put this back in there backwards and you come across it next time and you see this, you're going to go 1 propanol. You flip it over and then it says this, right? So you already didn't even know like what your flashcard was trying to do. So instead, there are a couple different ways that you could handle this better. One is to make a flashcard with the title on it. And on the side, I would say anti-Markovnikov hydration of an alkene. And then I would write like name of reaction. Because this is a useful flashcard, not because I'm ever gonna like test you directly over what do you call the anti-Markovnikov hydration of an alkene, but because we talk about it so frequently and we use these terms in class, this will help you follow along better in class. Now for actually learning the reagents and what they do, or you can put like question mark, write your reagents. Sorry, I'm just gonna start filling in so we don't spend too much time on this. And then on this side, I would write alkene to the least substituted alcohol or less substituted alcohol. So that is already conceptualizing, so that when you do go to apply this and you see an alkene and you see BH3THF, you think, okay, I need to make the less substituted alcohol, instead of going, okay, I saw this reacting with that 1 alkene and this is cyclic and now I don't know what to do. Or this has 10 carbons and I don't know what to do. You could also put notes on here like no carbocation rearrangement. Anytime that like there are probably common mistakes that you make when you approach this problem. Putting notes about that on the back side of the card can really help you. And so now this card is also useful both ways, right? Like there are gonna be situations where I give you the alkene and I give you the alcohol and I say, what reagent will do this? Or you're working on a synthesis problem in OChem 2 and you need to make the less substituted alcohol so that you can oxidize it to an aldehyde. and you can't remember what that reagent is. This flashcard is going to help you do that. So that's a good approach. And then another good flashcard that you can make, because I believe multiple flashcards for things is good, especially if they're testing you on different things. And then put your reagents here. What, I don't know why, let's just write them out again. pH3, dot, 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 dot. On the other side, you could do anti-Markovnikov, hydration, and then so the more ways that you approach this and the more connections you make, the better. So this is the way that I teach this, and a lot of students find it really helpful, especially when you get to OCHEM 2. You're going to learn in back-to-back chapters the exact same reagents reacting with a different functional group and giving you a wildly different outcome. And so students end up like making these flashcards that like just have reagents on them. And then on the other side, it says like Fischer esterification. But then like when they saw the flashcard, they were thinking of reacting it with a ketone. And so they come up with totally the wrong thing. You don't want your flashcard to be like leading you to the correct answer, but it should give you enough information that you know what the question is. And if you need to ask an actual question, that's fine. Just make sure that it's really broad and that you're not locking yourself into making a flashcard that gets you through one reaction and will never ever apply to something else. Because I think that's the main issue that I see. And also like, this is why going back through your notes and reworking the problems is not useful. You need to work new problems, because then students start to look for like this exact problem that we worked in class. And then when I switch up like one reagent, or I add in some different carbons, or like the starting material is slightly different, they lose it at the exam because they didn't learn this reaction. And they'll say that, and I'm like, you learned the reaction, but you didn't learn like how it works or like what it's actually doing. So
Right.
that's my input on flashcard formation.
Yeah. Oh, sorry.
Oh, no, that's fine. So like the rest of your question was more specifically about carbines, right?
Yeah. So my flashcards right now, they've been more like, for example, I guess this one, I did like, I had the name on the front, I did halogenation, and then on the back, and then I have at the bottom, it says like syn or anti-addition. And then I just put like, this was like, my flashcards right now were like all encompassing, and then I'm going to break them down once I have all the information together. And then I have the reagents, anti or syn addition on the back, and then like little notes, and then some examples. But yeah, so like,
Can I make a suggestion about that one real fast? The halogenation.
Mhm.
Add of an alkene, because we're about to learn halogenation of an alkane. And then in organic 2, you're going to learn halogenation of benzene.
Okay.
And halogenation of ketones. So like it's going to start being like really specific to functional groups.
Okay. Sounds good. Yeah, so I will keep modifying these. These are kind of like, because my notes in my journal were kind of everywhere with all the different ones. So I was like, I want like to have a card that just has all the information, or not all the information, but like most of like a good basis of information for that one. But yeah, my carbine card is very blank. So
Yeah, for this type of card, I would say like it sounds like you kind of have like a reference deck, right? Like this is kind of like a deck of like all the information organized. So like call that like your reference deck, and then have like a self-quizzing deck that looks more like what you just did. Because yeah, I don't think that what you did is bad. It's just not going to be like when you're looking at it. I'm not sure that it's going to help you come up with the information you need necessarily.
right.
But I think that's great. Like you took your notes and you organized them into something that works better for you, and that's really important. Can I see what you have on your carbine one?
All I have is that possible reagents are heat and light.
Oh yeah, okay. That's gonna kind of bite you in the butt for sure when we get
Yeah.
to radical chemistry because the reagents are heat and light. Okay, one second. I'm gonna remove your pen so I can see everybody again. Yeah, and that's the other thing is that like we haven't really talked about this yet because you don't know that many reactions, and so it's hard for me to say like, well, do you see like why this flashcard might not help you because it could look like any of these other things that you don't know yet.
Right.
Okay, so let's talk about carbenes. There are two types of carbenes that you learn. You learn one that comes from diazomethane and one that comes from chloroform. I think the chloroform one is really your more straightforward option. It's like a good flashcard for this would be um, like something like that that like tells you like these reagents together form something reactive. And then on the other side, right, like how to make dichlorocarbene and then draw the structure. So that's one way this flashcard is helping you recognize those reagents and what they give you, which I think is the hard part of the carbene stuff. Because once you actually have the carbene, most students are like, ah, it cyclizes, but it's recognizing this that most people don't do. So then another good example for this would be like for the actual reaction itself. So here you would be trying to come up with cyclopropane. Here you'd be trying to come up with carbene. And then I know, again, like carbene is something that some students just don't recall very easily. So maybe putting some examples of the carbene. Oops. Something like that can be helpful because if you see this, you can identify it as a carbene. You could just write something like, what are these, you know, or like functional group or, you know, reactive species, whatever. On the other side, you have carbene and it says structure. So if you grab that side, you're like, oh, okay, so that looks like a carbon with a lone pair and it can have two chlorines or it could have two hydrogens. Those are the two types that you know.
Right.
Is that a helpful approach?
No, this is for sure. I'm still a little confused on like not what exactly a carbene is, but kind of like how are we going to be using it in chemistry? Like if I were to have a problem that was like some mechanism involved a carbene, like how would I go about? Because there were some problems on the homework. I don't even remember what numbers they were, but I think it had to do with the carbene, and I was like, I don't even know how to use it, like the mechanism with it.
Oh, okay. I feel like what I was about to show you might not be as helpful. I was pulling up my notes so we could look at the species that are in here. Sorry, it's making me do a new share. Okay. So these are the handwritten notes. I don't know if I shared these with the class. I think I just put up the PowerPoint, but I can put up my handwritten ones also. This is what, like when I teach in person and I'm writing things out for the class, this is how I do it. I don't actually teach with PowerPoint. It just makes for a much nicer videos and shorter videos, so I'm not like writing everything out.
Mhm.
But so when you are actually doing reactions with carbines, there's always like a deprotonation step is the first part of it. So like diazomethane is made by first deprotonating. And you have to have a pretty strong base. Like TU toxide would work. Sometimes you see, TU toxide is probably the best option. But so you might start here and have to deprotonate it. Oh, I always forget that erasing on a PDF is not as easy. Okay, that's fine. And then this decomposes in heat or light because it's just not stable, and that helps the nitrogen leave the reaction because it's a gas, so it's just gonna leave. So I don't know what the homework question was asking you about, so I'm not sure how to address this, I guess, but it really is just the cyclic thing that you're seeing here. You have these electrons that are nucleophilic. You have these electrons that are nucleophilic, and you have a carbon that is fairly electrophilic. And so it is just a cyclic attack. You don't remember which problem it was?
No, but seeing this bottom part, just the mechanism of it makes a lot more sense.
Okay.
Just I wasn't really sure how it goes, like how it was, doing its thing, I guess. But that makes a lot more sense that it's coming, the pi bond's coming to the carbon, and then it's just, yeah.
Yeah, so the new bonds that you made, one bond is made from the pi electrons from the alkene. The other bond is made from the carbene electrons. Because even though like the carbene is able to be formed, the carbene is formed situ usually. Like it's not like you don't have a bottle of carbene. It's not stable enough for that. Like if you want to do a reaction with the carbene, you are first making it and then tossing in your alkene or whatever it is that you want to react it with. So that's why you learn it this way, is because like there is no like pre-bottled carbene. And that's also why it's so reactive, is just because it's so unstable. Like carbon wants to have 4 bonds, it wants to have a full octet. And currently, even though there's no charge on it, carbon only has 6 electrons. So it doesn't have a full octet and it doesn't have 4 bonds. So if you give it something that it can make that with really quickly, it's going to happen, and it's going to happen fast.
Okay, thank you.
Mm-hmm. I'll share these notes also, just because these notes do have like the full mechanisms written out, because this is what I would teach my class off of. And I know that the PowerPoints they don't have everything written out because I'm writing it for you as you're watching the videos. So yeah, I think they're actually probably already uploaded to our site also. And if you just went into the files, you'd be able to find them. But I'll put them. I didn't take attendance today. I had it open, but I didn't take it. Yeah, so there's a folder that says old 2341 notes. Yeah, that looks like where you could find them, but I'll put it like in the resources at the end of the chapter. Can't believe I didn't take attendance. I videoed the whole thing though. I could see who was here.